Cool, thank you everybody. Thank you for being here. As you can see, I'm going to talk about local first software. I'm going to talk a bit about what it is, what's different about it as a model. I'm going to show you it working, so I'm going to show you active-active replication between a Postgres database and SQLite embedded in the web browser through Elixir. I'm going to talk a bit about how we use Elixir and how that impacts the scalability and sync topologies that we can do. But most importantly, I want to show you how you can build local first applications on top of Ecto and Phoenix. And I do warn you, there is going to be some audience participation. It's not Doom robots, but we'll have a QR code, and I do have an ngrok link, and I hope that I will have the connection limit raised enough. Cool, so jumping in. How many people are familiar with local first as a model or a term? Cool. So, I mean, just to talk about what it is, there's a great manifesto. If you Google local first software by Ink and Switch, for example, basically what it boils down to is a model where your application code talks to a local embedded database in the client, and then state transfer moves into the background in the database replication layer. So you take the network off the interaction path, so everything just feels instant. And because you're doing the data sync in the background, it naturally means you're doing bidirectional replication, so you naturally get multi-user and you have to do conflict-free offline. And those kind of three things together are kind of a holy trinity around being able to craft a really optimal consumer or prosumer grade user experience. So if you look at systems like Figma, Linear, Superhuman, etc., they put an awful lot of engineering time and money into trying to being able to build systems to this grade. And what we're basically trying to do is just make that available for everybody to build off by kind of solving the challenges systemically for a whole range of applications. So this is us, we're ElectricSQL. We're basically Hasura for local first. So the idea is we drop on top of your Postgres, we work with your existing data model, you don't have to change your application at all, your back-end integration stuff all stays the same, but you get kind of magic local first on top. So you drop on our sync layer and you get live, real-time, conflict-free data in the client. So how does it work? We have a little animation, as you can see. As I said before, your application code basically talks to a local embedded database. We then have an electric sync service that manages the replication of data into a central cloud Postgres. You can use it to sync data across devices for an individual user. You can sync data between users, and you can control which data should sync between different clients and users. So you can do stuff by groups and regions or kind of sync globally. Wait for animation. And importantly, because it's all based on bidirectional active-active replication, you basically have to create like a live reactive application. So instead of doing static queries against your database, you end up binding live queries to your components. And then also, particularly with the model that we have, you have the ability to both propagate data out from central Postgres onto the local devices, and also you can aggregate data back from the client devices. So local first is all about user ownership of data, and you don't have to sync the data back to the cloud if you don't want to. But we built a system which gives you primitives to basically be able to control whatever kind of topology of sync that you want. So if you want to be able to say, have a whole bunch of people with data cached locally on their devices, but still be able to aggregate parts of it and do whatever you need to do as a sort of management layer or a control plane, you can do that through the system. And lastly as well, you can manage the evolution of the database schema but just by evolving the Postgres DDL schema. So I'm going to fire it up. I'm just going to try and hop out now into a demo, just show you a couple of kind of code samples, and then fire up a kind of silly example app, and this is where the audience participation comes in. So here we go. I have to change my display. Here. Okay, cool. So basically, this is a demo application where we're using a Phoenix application to write data into a Postgres database, and then we're building a local first web application on top of that. So as you can see, this is just like a standard Elixir application. These are the dependencies. To jump in here, for instance, and look at the data model, it's just basically ecto schemas. You have migrations. As per normal, you apply those migrations to the Postgres database, and the database schema kind of streams through the replication pipeline. And then what we have in here is we have a worker application, which is just a gen server that basically polls and works through the GitHub stars API, and we have a webhook controller, so when you add or delete stars, it comes through into the database. And so I'll fire that up in a sec, just to show you some side on the client side. So I know it's illegal to show TypeScript code in this conference, but we're going to do it anyway. So this is a React application. This is the kind of shim for kind of integrating Electric, all just sort of pulled into one file. What we have is we have a mechanism where the Postgres schema streams through the pipes, and then we turn it into a Prisma schema, and then the Prisma schema gets generated into Zod types and a whole bunch of additional stuff that allows you to have like a type-safe experience of working in the client just based on the Postgres schema. So if you work with something like TRPC, for example, you get a very nice type-safe experience for the client-side development. This just automates the creation of that based upon the ecto migrations. And then if you go, for example, we have a little widget here for pouring beers. It's a React application. This is a React component. This is a hook to basically get hold of an electrified database connection. So that's a SQLite database client that provides a Prisma-like API, but it supports live queries and live subscriptions. And then here, for instance, there's a query which is, we have a use live query hook, and then you have a live many, which is like find many, and you can basically write any SQL you want. So one of the important things about the system is that you're just dealing with standard open source SQL on both sides. You can do any Postgres with any SQL, you can do any SQLite with any SQL. We give you a convenience client functions on top of that, but you should just be able to express any complexity of SQL queries. There's no sort of special or kind of limited ORM. And then if you look at this widget, so the results for the live query just stay in sync. They stay in sync whether you change the data, whether somebody else changes the data. Anywhere in the world, it comes in over bidirectional replication. The component just re-renders. You don't have to do anything to do with moving state or establishing subscriptions or anything. Below, we then add a beer, for example, by just going db beers create. When that's created, the reactivity machinery just picks up on it. The component re-renders and updates the results above, kind of as you'd expect. So let me try and run this up. Let me try and fire this up. First, I shall get an incoming ngrok connection. I'm now going to fire up basically the kind of core replication layer. I'm going to do a Postgres database, our replication layer on our sync service. So if I just run a bunch of these services, this is our sort of local stack. All the code for this is up and open source, and I'll give you the repo link in a sec. What we can then do is connect into the database that we've just fired up. If we have a look at the data model, there's the kind of tables. We have the ecto schema migrations, and then we have the beers and the stars. You can look at, say, kind of beers. It's the kind of schema you expect. Here on the server, I'm now going to run the Phoenix server that accepts the webhook connections. And then I'm going to run the client application. So that just runs a web application. I was going to make a mobile application as well. We support mobile applications, but I didn't get time to apply the styling that I wrote to the web application. So let's have 2 Chrome windows instead. And so this is the kind of empty state of the application here, and it doesn't have any content in at the moment. If I now come, I've got a couple of mixed tasks. So first of all, I'm going to hoover down all the GitHub stars for our main repository. So let's go mix sync stars. That's going to just pull in batches of 50 stars at a time. That's going to come in, and the data just syncs in everywhere here. And then the principle, what I wanted to show was a pattern whereby, for instance, imagine that that's say content publishing data, like could be news articles or could be anything, or could be data that you might say aggregated for an analytics application. But what if you want then people to be able to interact and respond or collaborate on top of that information? So what you get is the information can come in from the central Postgres as a kind of publishing mechanism, but then here you get a local first interface, which just is naturally real time, syncs between all the clients, but also the data is syncing back. If I go select count ID from beers now, you can see it matches the number of beers that we've created in the app. And equally, if I go, say, insert into beers ID values gen random, you can see my 2-fingered typing at work. You see, you insert into the Postgres database, and it immediately reactively just appears in the local clients. Now what we have is if I've got another mixed task where I am now going to allocate everybody who has starred us on GitHub a beer, and those of you who we've been talking to about beer stars over the conference are now seeing perhaps how that fits into things. So let me just go allocate the beers. That basically pulls down, allocates everybody a beer, and everybody who started us already now goes into this smaller list of people who are allowed to come to our craft beer party tonight at a venue which Walter will tell you, which is in the Hoover app. And if you would also like to come to that, the moment for audience participation is here, because if you scan this QR code and star us on GitHub, you will appear in the listing, and I will automatically pour you beers and allocate them in the app. Not that we're doing shameless GitHub star hustling at all. They're coming in. Hey. Right, let me go. God, I can't keep up. Hang on. I guess I have to wait a bit for it all to come through. I'm going to try and catch you. There we go. Thank you, everyone. Keep it coming. There's an Easter egg in here where if we get enough stars in, a pizza appears. Honestly. This is fantastic. Keep it coming. I'm not going to move on to the next part of the talk until everybody stars the repository. No. Honestly. Can we shut that door? No. That's brilliant. Well, look, thank you all so much. That'll keep coming in. All the stars will come in. I will allocate everyone a beer. The event is in the Hoover app. Maybe I will carry on with the talk. So let me just get the display back. And here. Cool. So I hope that gave you a sense of, in a sense, kind of what's there and what's working, and sort of that's just one of the patterns that you can build with this. So we do have a particular take on local first, which is that we do build it with this like central Postgres as a kind of control plane, but you don't have to do this thing where you're syncing data to the cloud. You can also just have local data there. So you can basically manage the evolution of the schema, control which parts of the data are just owned by the users on their devices, and then which parts you want to sync on and off, or kind of between whom, basically. But just to step back out, I want to talk a bit about it as a development paradigm. So like one of the ways we think about it is local first as a kind of natural endpoint of the evolution of state transfer. So if you think about from back in the day how we started making web applications, you had web forms, then we got Ajax and we could do kind of fancier apps. Ajax kind of largely standardized on REST, and as it sort of standardized, you got a bit more kind of interoperability around the tooling. And then came GraphQL, and GraphQL was the first time really where you start to abstract the state transfer out of the application code. Because with REST, you're still basically standardized, but you're still doing imperative state transfer. You're going, I want to move this data over here, or I want to request this resource. With GraphQL, you've moved into a declarative paradigm where you're declaring what data your components need, and then the system is basically optimizing, compiling up the fragments into a top-level query to optimize the network transfer for that kind of route. With local first, it kind of completes this picture of just fully abstracting state transfer out of the application code. And as well as optimizing, say, the network fetch, once you have it in that kind of declarative mode, you can optimize everything. So you have like transfer, placement, retention, subscriptions, consistency, data integrity, resource uses, right? And there's trade-offs between all of those things in different systems. And if you're building a system imperatively, you're just making a whole bunch of assumptions about how your application functions with regard to those aspects. Whereas once you move it fully into a declarative domain, as per some of the research that I'm showing you here, these are a bunch of papers from a very cool project, a US research group called the Hydro Project, based at Berkeley around Joe Hellestein. The bottom paper on that list, New Directions in Cloud Programming, is where the quote comes from. Like, they're basically building out towards a next generation operating system for the cloud that is all built on top of this kind of more declarative picture of declaring what your application needs, what data needs to be where, and then just letting the system take care of it. And as we know now with things like ChatGPT and large language models, what's going to be optimizing that system? It's going to be this crazy AI stuff that's emerging. And you have both optimizing these concerns like, say, data transfer and placement can be moved into a domain that can be optimized by these AI systems. Also with local first, you have, as I'm talking about, like user ownership of data. And you're going to have things where those kind of models are going to do federated learning on, for instance, your data. And so if you have your data in this type of system, and those models can create adapters, which is one of the great use cases that they've already seen for GPT at the moment, is to create adapters and do these kind of ETL pipelines. They can kind of do those on the fly. You have a whole new sort of type of data infrastructure where people are providing services and building insight whilst you still actually retain your information in your local applications rather than siloing all the information behind cloud-first systems, which is what happens today. So that's some of the big picture, which I think is pretty cool. But I want to talk a bit more pragmatically around some of the just practical concerns around, say, moving to this as a development paradigm. So 3 things I'll just highlight. One is that you basically lose the back end and the kind of consequences of that for how you build applications. Another one is how you can control what data syncs where and how that affects your ability to make applications. And if there's time, I can touch on some stuff around basically having to operate at the far AP side of the CAP theorem. So just practically in terms of losing the back end, you don't have somewhere where you're just writing, say, sort of procedural back end code to say, I want to kick off an email sending or do this background process. So you have to move that type of stuff behind event sourcing or database change events. There's a whole bunch of ways of doing that when you're building on Postgres or building in Elixir. Highlighting 2 here. One is OBAN. So OBAN typically provides you the nice kind of OBAN namespace functions to insert jobs with your back end code. You can, of course, just write directly into a table, and you could do that either through a trigger, or you could do that directly in your client code. So you could just write a data record in the local SQLite, and when that streams through and replicates to the back end, it'll trigger the background task without having you to change anything with your OBAN wiring. I think Lars, who's somewhere here in the audience, he made a great demo with Canafile of wiring up ElectricSQL to a live view application. So Canafile wraps the native Postgres logical replication, which our system also works with, and you can basically just pick up on live events in a Phoenix application as well, just through that. Or you can go the whole hog and do something like Materialize, which is maybe a much more advanced streaming database. Super cool, won't talk about in detail. There's also a talk I know coming up on Debezium, which would be another tool for doing like change capture off the back of the database. So that's how you in a sense sort of have to adapt to doing like server-side workflows. One of the other things is you lose this kind of trusted execution environment for stuff like authorization logic or validation logic. And so typically, like systems like Couch and Firebase and stuff that I've done for a long time, you have to move some of that logic into a sort of database rule layer. With this type of stuff, you kind of immediately think of, say, row-level security within Postgres. It's not quite the solution because you actually need to bring the kind of context of the client connection. So you need like an auth context, which is what, say, Supabase brings on top of row-level security. But you also have challenges around like the scalability with connections to the original database, because if every connected client is executing the authorization logic in the database, then A, you need to hold a connection open for each client, and also you're adding a whole bunch of load into the database layer. So what we've done is we've designed a system where this is a sort of summary of our component architecture. You have Postgres on the left. We have this Elixir-based electric sync service in the middle. Basically, we have its logical replication, comes through to a decoder, goes into a replication stream, and we do basically authorization, validation, and filtering within that service. And then you have a protobuf connection into the client, which is the kind of replication connection between the SQLite and the back end. What that means is we have typically 2 connections to Postgres per electric sync service, one just to do kind of normal SQL interactions and one for a single replication stream. And then you can have as many clients as you want connected into the Elixir service because it's naturally very scalable. So here I'm just sort of illustrating, say, if you want to, it's horizontally scalable. It's slightly stateful as a sync service because it buffers information that you need to tolerate things like disconnections and stuff. So there is like data persisted on disk and memory, but that data is rebuildable, so it's not like a source of durability. So you can basically treat it pretty much like a stateless web service, so that's horizontally scalable. So you can get up to like 100,000 or 1 million live connected clients fairly sensibly by just, say, scaling out a number of the sync services and having something like maybe 1,000 clients connected to each, which is quite radically different to what you can do with systems like, say, Supabase or Hasura today. And just on the same sort of topology, so it's active-active replication. So in a sense, every node is a source of truth. But Postgres is the source of durability, and we've made the system so it works with any Postgres that does logical replication, including things like Aurora and AlloyDB. You have this sort of rebuildable cache within the sync service, and then you have the constraints around like network and storage for what data you can store and transfer on and off to the local device. So this is kind of why you need to have strategies around subsetting the data if you have a pattern where you have like a larger central database, but you want to get smaller sets of the data onto the local device. And this has kind of been, it's been quite a big focus of the project. So we've looked a lot into this, and we've done quite a lot of engineering to basic and design work to come up with a model to allow you to express this kind of full range of sync models. So ephemeral queries on the left-hand side is kind of like the standard model of just an online system. You make a query to the server and you get the data back and you sort of render it. Pinned queries is the thing where you say you do that, but you cache the data. And that would allow you to do something like if you say you've checked a page to see the weather, you navigate off, you hit back, the data's still there, so you can still kind of, you can see what you've seen before. Live queries are where you do that, but you maintain a subscription. So say you've checked the weather, but the weather's updating in the background, you would maintain a subscription to that information whenever you're connected, so that you can keep the data that you're able to view kind of updated. On the far right-hand side, you've got whole database sync, which is the sort of simple case of just it syncs the whole database. You're not doing any of this kind of subsetting. But the two here around content-based and schema-based sync is where you introduce sort of proper partial replication. And for local first apps, the sort of really what you're trying to do is go beyond just, say, caching data offline. Instead, you're trying to provide full interactive functionality, and you may want to sync more data than you're currently showing so that you know that the user can navigate to other parts of it or kind of interact with other parts of your application. And then you can think about that either as like schema-based, which would be sync this namespace, sync this table. Then content-based is when you do row-based filtering with that kind of authentication or client connection content available. And so what we've designed as a system is basically, we call it shape-based sync, and this gives you an example of the front-end user experience. So we, on the back end, there's this sort of DDL side authorization step. So you can add certain rules to say which tables are allowed to be exposed to this system. We say which tables are electrified at all. And then you have some rules for like authorization and permission scopes. But then the control of actually kind of in what units and what sort of shapes of data sync onto the application is given to the front-end developer, because actually they need to be able to sort of adapt that and adjust that in order to craft the right user experience. So instead of like a database admin defining some DDL rules that control your application's user experience, as a front-end developer, you want to say, oh, actually, I need a few more fields here, or I want to sync the author as well, because I do want them to be able to go and access that offline. So that's what this sort of shape-based sync kind of API on the front-end stuff allows you to do. The example here with the data model is, say you're building like a project management app like Linear. You have, say, projects or a workspace, and under the project you'd have like open issues and they have comments and so forth. When you say, right, I want to sync that project in, you kind of mean I want to sync all of the data underneath that project so that you can interact with everything in that kind of project or workspace. And so you can imagine like deep kind of tree-like shapes. You can have kind of wide, narrow shapes. But you can basically define those using something that's very similar to like doing an ecto query with preloaded associations. So this is based on Prisma syntax, but it's similar with like an include graph, which is very similar to the kind of preloaded association graph. But instead of just being a query, this defines data which is then maintained in and synced. And you have, at the bottom, it's showing you the retained semantics. So do you want to keep this data live? What's like the priority if there's contention for the storage space, etc. So you have APIs to sort of express a bunch of the edge cases that you'll encounter around how you keep data locally. And then you go beyond that, and it integrates with the component system on the front end, kind of in a similar way conceptually to the way that GraphQL works, as I was describing earlier. So with GraphQL, you have these fragment containers that are declaring which data is bound to which component, and then there's a hierarchy of those, and the compiler kind of aggregates that all up into a big bundle for the top-level fetch. And what we do is the same thing. We allow you to just make direct SQL queries from any of your components to the database, and then we can derive out an aggregated shape which is required to sync in order to fulfill that component hierarchy. and then you can put boundaries in some of the sync behavior. So on the code sample here, where it's saying it's a React component to show a project, you put a sync shape component with the configuration for what you want to sync in there. And then in a sub-component, we have a hook to then access, for instance, the issues that were part of that project. And you can either access kind of so you can basically filter your queries automatically, but you can also get a handle on, if you imagine that tree and you sort of divide it up into segments, you could say this top bit syncs and is sort of shown above the fold, and then these bits are going to sync in next. And so you can have a component which can access a handle to then trigger the sync on a subset of the data. And then another interesting complexity of the model in terms of how you control, in terms of this sort of partial replication, is a lot of applications you'll have content, but you'll also have listings and discovery. So a classic example would be some sort of geo-filtering, or this is full text search. And so how do you do full text search without syncing the entire table onto the device? So say you were trying to search across restaurants in the whole world. You don't want to have to search, you don't have to sync all of the restaurants in the whole world to do sync, to then just sync the one that you actually want to kind of get the information on. And you can do that kind of shallow, wide shape. But for instance, if it's a full text search index, it could be very large. And if you've got 100,000 records, again, it's far too much data to sync. So what you really need is you need a mechanism to query the central database and then kind of have the result set sort of in your local database. If you query out of band, you run up against consistency issues. So with this type of stuff, the data that will have come through your replication stream and synced into your local database will be at one snapshot. If you then go and query out of band through just a web service to a Postgres doesn't do snapshotted queries, so you're always getting the latest data. So how do you mix that data into your local database? It's a really hard problem. So basically, we've designed a system for doing discovery queries in Paradigm. So you send this through our you basically send a request to establish a discovery query through the replication protocol. That gets run against the server-side database. The result set is then turned into a shape, which is maintained as a shape that you sync. And on the server side, we monitor the replication stream to know when we need to rerun the query to pick up on new content. So it's a slightly heavier thing in terms of impact on the database server side. But from the front-end perspective, it just allows you to do basically arbitrary queries through to the central database and still then maintain the data locally in sync. How am I doing on time? Am I good? Cool. I've got a couple more quick ones and then just an end slide, or I'll wrap. Okay, I had a couple on like this sort of cap theorem stuff. The AP side of the cap theorem has become much, much stronger over the last few years, thanks in part to a lot of research in Europe that's been pioneered by the academics on our team and my co-founder, Volta. And there's some really interesting challenges where both like maintaining, say, SQL-like constraints and referential integrity in a local first system is hard. When you mix in partial replication, you have partial replication boundaries, it becomes even harder. There's a bunch of stuff we're doing around that. Ultimately, though, all of that complexity, what we're trying to do is basically take that complexity, keep it in the box, and deliver this. So it all wraps up to the proposition where you can come along with, say, an existing Phoenix app with Ecto migrations, you drop on some annotations to your DDL using Ecto migrations, and everything just works and the data is there in the client. And one thing I just want to flag up is we've recently opened up a call for design partners. So if what we're doing sounds interesting, this is still early stage and there's lots of this, there's stuff that's working and there's a lot of this that we're still building out. If you're interested in collaborating with us along that journey, we'd love to hear from you. And you can see this website here, next.electricsql.com. If you take a look at that, there's a form you can get in touch or just come and speak to me or Volta. Thank you.
Thank you so much.